Okay, our next problem we have tennis players basically volleying off a garage door. So we've got 16 tennis players, a certain number of tennis players, I'm going to call it N. Mass of the balls, and there's an incoming velocity of the tennis balls, an outgoing velocity, and time between volleys. So let's get rid of Jack Bauer here. And what we have is, let's see. So you've got N tennis players. And delta t time between bounces per player. U is what I'll call our impact velocity, and V is our rebound velocity, or more correctly, impact speed. And V rebound speed, and M is ball mass. Okay, so what you have here is this, tennis players. There's your garage door. Here's the tennis player with his racket, and the ball goes bonk, and it comes back. And the player hits again bonk, and comes back bonk, comes back bonk, comes back, etc. Does this every delta t time as the time between bounces. So it's bonk, and delta t passes bonk, delta t bonk. They come in with a speed of u, and they leave with the speed of v, both horizontally. The mass, we got the mass of the ball, of course, and we want to know, what do we want to know? First is the impulse imparted to each ball, I think. So the balls come in. I'm going to call this P impact is what I'm going to call the momentum of the ball just before it hits the wall. Okay, so the garage door, that is. Okay, so there is our positive x-axis. So it's got a speed of u. It's going positive. So its velocity is u, and its mass is m. So its momentum is going to be m times u. Okay, this is the ball. Its mass m. Bonk. Okay, and then the rebound velocity is the velocity it has as it comes away. Okay, p rebound, which I'm going to call, which is then its mass is still m, and its velocity, well, it comes away at a speed v, but now it's going in the negative x direction. Remember, speed is just the magnitude of velocity, so its velocity is actually going to be negative v in this one-dimensional case. So that's the rebound. So the impulse on a ball, for each bounce is going to be the velocity after the bounce, the momentum. The impulse on the ball is going to be the change in momentum. All right, so that is going to be the final momentum after the bounce, which is the rebound momentum, minus the impact momentum. Okay, so the impulse on the ball is going to equal, we will say, right, so it's going to equal negative mv minus mu. And so the impulse on the ball is going to be negative m u plus v. So if you think about this, so the mass of the ball and the total change in velocity is going from u this way to v this way, right? So the total change is u plus v. So you see it's got to go through a change to get the u to 0, or to get from u to 0, and then another change in the same direction to get from 0 to v. So that is the impulse on the ball. Now let's see what we were asked for. What is the impulse a single ball exerts on the garage door? Okay, so this is the impulse on the ball, which is the impulse the door exerts on the ball. So the impulse on the door, so let's switch to blue here. Impulse on the door is going to equal the negative of the impulse on the ball, because this is the Newton's third law pair. The door exerts an impulse on the ball, okay, like that, which means the ball is exerting an impulse on the door. So for the door to bounce the ball back, well, when the door bounces the ball back, the ball, gives the door a shove that way. Okay? Negative I ball. Okay, so the impulse on the door is the negative of the impulse on the ball, which is going to equal m times u plus v. So let's see. That is for us here, m times u plus v. So we have 4.2 plus 3.2. That's our u and v, and then 0.10 kilograms. Let's try that. 0.10 kilograms times 4.2 plus 3.2 is 0.74 kilogram meters per second, and a kilogram meter per second. So this was 0.10 kilograms times 4.2 meters per second plus 3.2 meters per second. And so that's going to equal 0.74 kilogram meters per second. And a kilogram meter per second, let's remember, is the same as a Newton second. 0.74 Newton seconds, because a Newton is a kilogram meter per second squared, multiplied by the seconds, okay? And then you cancel one. So, let's see, 0.74 Newton seconds. Let's hope. 74, and there we go, boom. Okay, now what is the average force exerted on the door by all of the bouncing balls? So this is where it gets interesting. This is what one ball does to the door. This is the impulse one ball puts on the door. And now we want to find the average over the whole, over the whole time for all these players. So let's think about this. Here is, let me go to another color. Let's go with purple. Okay, so here is, say this is our little force versus time plot. Okay, for one ball hitting the door. So most of the time, and now I'll do this in red. Okay, most of the time the force of all exerted on the door is 0 because it's not touching. And then it has a little spike. It goes boom. And that does that. And then after a little while later it goes boom again. Okay, the time between these spikes, so we're going to say from like the beginning of one spike to the beginning of the next one, roughly, is delta t. And we were given that, it was like 3 point something seconds, okay? So over this period of time, you get this one spike. Okay? So if we take, and the area of this spike, as you'll recall, the area of this is the impulse. So this is a plot of the force that one ball exerts on the door over time, and the area under that hump is the impulse it exerts in one hit. So it comes in and goes bonk, and then it's off here, the tennis player hits it again, it comes back, hits the door, bonk, again. So the average force over this whole period of time, which you're going to say is a dotted line there, is going to be this impulse divided by delta t, right? Because impulse is average force delta t. So this I door here is going to equal, so F average is going to equal I door over delta t. So that is for, now that's the average force exerted by one ball, remember? Or one tennis player, one ball, which keeps going bonk, 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 bonk. But we have n tennis players with n balls. And tennis players with n balls. So the true, you might say the total average force is going to equal the number of tennis players with balls going bonk, 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 times the average for one ball, which is what we calculated up here, right? This is just one ball hitting every delta t. So this is actually going to be, the total average force is going to equal n times I door, which is the impulse, one ball exerts on the door and one bounce divided by delta t. So let's see, so our I door was 0.74 Newton seconds, right? And that was our previous answer. And then our delta t was, let's see, delta t was 3.4 seconds. answer divided by 3.4 seconds times 16 players, and that's going to be 3.48 newtons. Let's see. Yes, wait. Yes, correct. And where I was trying to go with this kind of silly, problem, is that this is actually a lot like what gases do. We have molecules of gas, bouncing against a wall. So you've got the wall of your container here, whatever, with the gases in it, and you've got a bunch of gas molecules, little spherical, whatever shape they are, gas molecules, and they're bouncing off the wall, one after another, boom, 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 and it's a bunch of these little impulses. But when you have a huge number of these things going over and over and over again, it basically, acts like a consistent force. So you might have, like, if your force on the wall versus a time plot, if you have just a few molecules, you get, like, see how this boom, 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 whatever. And the more you have, the more steady and regular this becomes, and it just sort of blends into effectively sort of an average force. And the more molecules they have, the smoother it's going to look. That's where I'm trying to go with this whole, tennis players and tennis balls thing.